We've been doing this in the right order, by the way. No. I mean, that's the thing we're going through today in the lesson. In a way, we've been teaching these lessons in the right order because I think you'll see the warm-up today has prepared us very well to consider what's about to happen here, okay? All right, so this is, I think the first problem on here. I think this questionably matches up with my PowerPoint. All right, so we're gonna. I think this is example 1A. Do I have? I want to make sure I have the same things here. I don't know. All right, well, we'll do this one, and I don't know. You'll have to judge where these things correspond to your packet. Yeah, it's very similar. Except notice in the warm-up today there was no sense of time at all, right? There's no time involved in the warm-up, right? The independent variable in the warm-up was R. We were changing things with respect to R. Yeah. Is this not the first one?
No. Still 45%. It's not in our packet.
All right, well, this is number 1, part A. It is number 1, part A. It's worded a little differently. But we'll all right, it's not in the packet, whatever, okay. We'll end up answering 1A along the way, though. All right, so consider sphere of radius 10, just like we did. How fast is the volume changing with respect to time? Notice time, with respect to time, notice we're asking questions about fast, slow, right? That was not in the warm-up at all, but it does seem similar, perhaps. If the radius changes at a constant 0.1 centimeters per second. Okay, so notice that here the independent variable everywhere is time, and everything is changing with respect to time. Well, I shouldn't say everything is changing with respect to time, but, well, I think everything in this problem is. Okay, so let's give some names to these things. I think R is a good name for 10 centimeters. The thing that's given, what would you like to name that? Can you come up with a really mathematically savvy way of naming that? The rate of change of the radius with respect to time. What would we call that? What would you name? What is the thing? We're in calculus class, remember. That is the radius, the change of the radius with respect to time, the instantaneous rate of change of the radius with respect to time. Yeah. How about dr dt? Is that what you were going to say, Haley, too? Dr dt is 0.1 centimeters per second. And in all these problems today, I am actually going to carry the units along. I think it's going to be useful because of the nature of these problems. And the only thing left that we seek is what? What would you like to name the thing that we're missing? Using the same Caduce move that we just did a second ago, we might call it dv dt, right? Is the thing we seek. The change in the volume with respect to time, the instantaneous change in the rate of change of the volume with respect to time.
There's a hair in it. Whoa.
There you go.
Throw it over here on the trash.
All right. The thing we'd love to have, friends, is an equation that relates these things. I do have an equation that doesn't relate these, though, that we learned about from someone who said it earlier. Between the volume and the radius. I don't know what the relationship between dr dt and dv dt is. But I do know the relationship between, like, the pre-calculus style, non-changing things. And that's v equals 4/3 pi r cubed. We've not done any calculus yet. That's like a pre-calculus equation that relates the things that aren't changing, v and r, to each other. But we can get, anytime we need it, an equation that relates the rates instead by taking derivatives. Now be careful here. We're taking derivatives with respect to time, everywhere. Not r, but with respect to t. So, of course, the derivative of v with respect to t is just dv dt. And help me out with this side. Of course, we get, just like we did in the warm-up, 4 pi r squared. But careful, if we're taking the derivative not with respect to r, what else do we have to say? Times well, let's give it the name we've already given it today.
The RDT.
The RDT. What's that called? I forget. What did we just use? The chain rule, right? That's the chain rule. Just want to make sure that you see that we just used the chain rule. Why do we use the chain rule? Because we're taking the derivative of everything with respect to not r, but with respect to t. Right? So if I asked you what's the derivative of this with respect to r, you would say 4 pi r squared, full stop, right? But if I asked you what's the derivative of this with respect to q, you'd be like 4 pi r squared r dq or something, whatever the other letter of interest is, right? Well, now, I don't know, the game is up, isn't it? We now have a relationship between these three things. We know two of them, we don't know one of them, so figure it out.
No, wait, don't take it out of the way. They're standing in the way.
Sorry, did I just put, this is supposed to be 10. So, well, we've thought about this in a different way. And actually, I'm going to make one more revision to what I've just typed, what I've just written up there.
Wait.
Yeah. I'm going to use the actual units here, just to make a point here.
Wait, don't you mind it?
All right, so what do we get? Of course, the interpretation and the way we did this is similar to what we did in the warm-up today, but it is different than the warm-up, but the computation is the same. Of course, what do we get? 40 pi. What are the units, friends? What do we get?
Centimeters.
Centimeters cubed per second. All right, so this is your first encounter with something called a related rates problem. And that's a good name for this problem, this kind of problem. Because the equation that we sought out to solve this problem is an equation that related to rates. You like that name for it? So, and what was what did we do? Well, we wrote down things we know, just like in any math problem, things we know and things we want to find. We related them using something like pre-calc / geometry, like from a previous life. And then we turned that into a calculus tool by using differentiation with respect to t, which always requires chain rule. So this is a little different than the table that's on the front of your, the outline that's on the front of yours. I just think it's a little messy. Eventually I'll update this little sheet that comes with here. But so understand the problem is like the first thing I would do. You saw me doing that by identifying the rates of change I see and identifying the rates of change of the thing we know. We're going to develop a mathematical model. A lot of times it didn't really need to be happening on the first problem, but a lot of times it will involve drawing a picture and using a lot of geometry principles of various kinds. This second italicized yellow line here is, I think, super critical. Be sure to distinguish, it says, constant quantities from variables that change over time. Now in the first problem, as time was moving on, the radius and the volume were changing. But in some later problems that we'll do, for example, we have a cylinder and the water level in the cylinder is going down or something. Notice what's changing there, of course, the height, the volume, but what's not changing?
The radius.
The radius, right? So we need to be very careful about things that are changing and things that are not changing in the problem. We haven't encountered that situation yet, but just be warned, that's going to be like an important element of your life. Only, well, we won't read that. Okay, write an equation relating the variable, like we did earlier, to the variables that we want to know. That was v, in the last example, that was v equals 4/3 pi r squared cubed. Excuse me. And then, I have another slide. Step 4, what are we doing? Differentiate implicitly. And the chain rule will be especially critical. It won't always be at play per se, but if you have some function of r, like on the last problem, then it will likely be at play. It will always be your friend here along the way. Substitute don't substitute beforehand, right? You substitute beforehand on the last problem, you'd be like, oh, 4/3 pi r times 10 cubed. What's the derivative of that? 0. Oh, wait, hold up. Hold up. 10 is a thing that is not, it's not always 10. It changes, right? R is not 10. R happens to be 10 for one moment, but R is a thing that changes. So you can't just plug them in ahead of time. You can only do that safely after having differentiated both sides of your equation. So anyway, you saw us doing this. Finally, make sure you use appropriate units and interpret your answer. Make sure you actually answer what was asked, too. Did it ask for on the first problem what the rate of change of volume with respect to time was? Yes, okay, and that's what we reported, and that's what we boxed our answer. Okay, good. We got the right units?
Yes.
The units, by the way, should make sense in two ways. They should make sense from the mathematical analysis, right? It came out, we could have feed this to a machine and they would have gotten centimeters cubed per second, even if they had no idea what meaningful application in the real world that had. But it should also make sense from an intuitive standpoint, right? What should, before you even do the problem, what do you think the units should come out to be for the change of a volume with respect to a time? Of course it should come out to be something like units of volume divided by units of time. All right. So now I think we're finally on example 1 here, A and B. This is the one we just did. dv, so there's nothing to say here. I'll just write it again. dv dt equals 4 pi r squared dr dt. All right, this is an interesting problem, though, with a cone here. Do we know the formula for the volume of a cone? You do. Good.
1/3 pi r squared times the height.
How do you remember that?
I see you did a cool thing when he was showing us that it actually is 1/3.
Oh yeah, every geometry teacher should be required to show people, I don't know, with sand or water or something, that like 3 cones
Yeah.
of radius, of a certain radius and height together fill up exactly a cylinder with the same radius and height. Right. It's like 1/3 of the cylinder that encloses the, and that's true of any prism. Do you remember that? The formula for the area of any prism is 1/3 times the base area times the height of whatever the prism is. Is that a thing you remember from geometry? For the height of any pyramid. It's the same thing. It's always 1/3 of the volume of the cylinder that the prism that encases that pyramid. All right, whatever. It's not important. Take a derivative. What are we going to need here? Keep in mind that we have 3 variables, all of which are changing perhaps with respect to time. So I'll do the left side. There you go. You're welcome. You do the right side. Be careful. Again, we have 2 functions, both of which change with respect to time. Everything's at play here. What are we going to need along the way? Can you just say it? Thank you. Yeah, both. Product rules we're going to need here. So let's take the derivative of this thing. First, supposing that, I don't know, h stays constant. So that's the derivative of this thing. And then times just h, right? The first derivative first times the second. So what will that be? By the way, the 1/3 pi could just come out of the whole mix if you want, right? So let's just worry about r squared h. What's the derivative of that? Well, it's 2 RH dr dh. And do you see, dr dt, excuse me. Do you see that h just came along for the ride that time? H was just like a placeholder. But we still need to do the product rule, so what's the other piece there? We're doing, that was the derivative of r squared times h. Now we need to do, what is it? The derivative of h times r squared. So that's r squared times, well, the derivative of h is just dh dt. Please ensure that you understand every symbol on the board. Feel free to multiply the 1/3 pi in or not, whichever. Yeah.
Isn't there some point they could like substitute out the h?
Yeah, we will do some of that too. Don't spoil it, though, like that. Yeah, we will do some other things with this, but this is certainly a thing we can do. I think we're back on track though, right? We're on this packet. We did A and B, example 1. Look at that. Flipping the page. Where are we now? A rising balloon. Okay. A hot air balloon rising up from a level field. Well, the picture, and unfortunately, a lot of the work is here. I feel bad. So we'll work through this as if you don't know how to do it. But it gives you like everything on there. So again, I need to type a new notes sheet that doesn't give everything away like this. Right, Alex? Haley? Does that make sense? Right. Haley? All right, so the picture is drawn pretty nicely here for you, but hopefully you see why. Do I have a second one on this? No, I do. Okay. Why the picture needs to look like this. Here's the balloon going up in the air. It's going straight up in the air. And over here, this is an observer watching the balloon go up. And it's 500 feet from the liftoff point, so we can label that. And now we need some names for things. I guess we'll use the names that are in there. We'll call this H. Is that what it has for this side? Did it give a name to this side? Okay, doesn't matter. We'll call this theta. Now, before we go too far, just looking at this picture and understand the situation, what is it that changes here? The angle definitely changes. What else changes? The height definitely changes. What else changes if you cared about it? The hypotenuse does change as well. What doesn't change? Yeah, this 500 will always be, regardless of what this triangle looks like, this side will always be 500. Is that clear from the problem statement? Okay. All right, good. So, do we have an equation that relates theta to again, not a calculus related rates equation yet, just an equation that relates the things in this picture? Yeah, just a pre-calculus equation would be that the tangent of theta is equal to h over 500. Right? Now, you can manipulate that a little bit if you like, or you can just take the derivative right away here. If you want to say 500 tangent, I don't know. Doesn't matter, whatever. We can do that. We never did write down the things that were given or anything. So theta is pi over 4. What's 0.14? Yeah, it's d theta dt. And we seek what? What do we seek? What name do you want to give the thing we seek? Read the question. How fast is the balloon rising at this moment of interest? So that's the h dt is what we seek. Yeah. So we need to take now we need to do some calculus to get an equation that doesn't relate h and theta, but that relates d theta dt and dh dt, then possibly uses theta too. Right? So let's do that. So what is over on the, again, I'll be a nice person, I'll do the right side for you. There you go. The derivative of h with respect to time is dh dt. There you go. What's the derivative of tan theta again? 500 times secant squared theta times, squeeze it in there, chain rule, d theta dt. And now we finally have an equation that has the three things we need in it, one of which is unknown. So go ahead and plug it in. What is the secant of pi over 4? What's the cosine of pi over 4? The secant of pi over 4 would be just root 2, so that kind of works out nicely because we're going to square it, right? Yep. 0.14 radians per minute. Let's just make sure the units come out right here. Per minute. And this was 500 feet over here. So even without a calculator, I think we do a pretty good job of working this out. The writers of this problem knew this would work. So we have 500 times 2, so that's 1,000 feet times 0.14 per minute, radians per minute, but that's unitless. So finally we get for dHdt 140 feet per minute. So you catch the algebra, the calculus, the unit analysis? Everything okay there? So I don't know how that relates to step 4, step 6, step whatever they have on there, but whatever, we did it, okay? I was looking at the thing. Just like optimization, the reason we have 2 days on this too, there are so many varied situations that we're going to deal with volume, deal with. Pythagorean theorem is going to come up, but all sorts of different situations. So we have to just expose you to as many problems as possible. All right, so here we have a situation nicely depicted here. If you get a chance to read it here. We have a police cruiser approaching this intersection, chasing after this car, which is going that direction. They're rounded. This is a chase scene.
Wait, so police car going down or across the highway?
Police, the arrows on here are marking this pretty well.
Police officer is down.
So in this situation, just right off the bat, what changes? If you like the letters here, let's use them, X, Y, and Z. What's changing? Z changes.
Why don't X also change?
X changes. Y changes. They all change here. It's okay. It's not a problem. X, Y, and Z are all things that change. Let's also say in what way they change. Y is something that has like dy dt is going to be what kind of value given the way that it changes? It will be a negative number. Dy dt is a negative number. I haven't even looked at the problem yet, and if the police car is coming down this way, I know this segment is decreasing in length. Similarly, dx dt is something positive, right? X is increasing, we could say, or dx dt is a positive number. Z?
Maybe it's not changing.
Z is not obvious what Z is, actually, is it? On the face. We're not sure, maybe at first, maybe we have a hunch. But actually I'm not sure right away, just from this picture, whether Z will be positive or negative. dz dt will be positive or negative, yeah.
Okay, so.
And then,
Police car.
finally, what's the thing that relates X, Y, and Z? Pre-calculus style. Yeah, the Pythagorean theorem obviously is the thing that we're going to be differentiating. All right, so let's use all that and go toward
so
it.
like, does it specify like how fast both the cars are going? I can just see that.
It does. It's on your paper right in front of you.
Oh, yeah, I know, but like.
The problem says that Z is increasing.
It tells you that. That was nice of them. Yeah. But if the police car is going toward the intersection, I don't think they had to tell you that, is all. Should make sense that it's decreasing, therefore dz dt is a negative number.
It doesn't say how fast the car is chasing is going.
All right, well, let's start writing down everything we know here. Okay, so cruiser, so this is y, I guess, is 0.6. X is 0.8. D, what does it say? Between them, and the car is increasing at, the distance between them and the car is increasing at 20 miles per hour. So what's that? That's dz dt. It makes sense that if you're the police officer that maybe you don't know how fast, you don't know dx dt, but you do know, because you've got a radar, you do know how fast it's moving away from your radar, right? That would be dz dt. So that's 20 miles divided by hours, if you want to write that. The cruiser, it knows, of course, the police officer knows his own speed. That's dy dt. And what are we saying that is equal to? Yeah, negative 60 miles per hour. And the thing we seek is dx dt, the speed of the car. Of course, that's what we seek. Okay. And then someone already told me that x squared plus y squared equals z squared. Differentiate it with respect to time now. Are you ready? Someone just run through the whole thing for me.
Why is it negative?
What? Oh, because, oh, I'm sorry. Yeah, negative, dy dt is shrinking, right? The dy dt is a negative number because y is decreasing. Yeah, so careful with that. Johnny, go ahead, sorry.
2x dx.
Yeah, we've got all these things popping out all over. I mean, come on. If we're not having fun, I don't know what to tell you. I mean, we're having change all over the place. It's fun. The 2's could go away if you like. That's fine. And well, we don't have to make the 2's go away yet, but this is great. We're having a great time. We're going to substitute everything in. There are 6 things to substitute. There's 6 variable quantities, I guess, in here. So we have, we just need to find dx dt. What's the snag? Those who are already starting to do it. We're missing. We also need something else, don't we? Seems like we have everything we need except, I expect dx dt to not be something I substitute in. I have x, I have y, I have dy dt, I have dz dt, but I do not have z. So, at this moment, frozen in time, do you think you could tell me what z is, though?
Yes.
Yes. What is it?
1.
How did you get 1? Yeah, it just so happens that this is a Pythagorean triple. 3, 4, 5, 6, 8, 10 is a Pythagorean triple. So that worked out nicely. Again, they're making this nice for us. It could be something terrible in a problem that you might do. It could be something terrible, but it came out really nicely here. Now, even though that wasn't given, we have it now, and now we can go to make our substitutions and solve for dx dt. So let's do it. 2 times 0.8 miles times dx dt. Let's just drop all the 2's right now. Plus 2 times 0.6 miles times negative 60 miles divided by hours equals 1. All right, so we really do only have one unknown here. Sorry. Weird. Oh, did I get? Yeah. I did it elsewhere and forgot that. All right. There's our equation. Everything works out pretty nicely, maybe. Let's check it out. Over here we get, check the units on this here too. This is, over here we get miles squared per hour. We get 20 miles squared per hour. Over here we get negative 12. Negative 36. So if we add that to the other side, what do we get here? Is it 56 or 5.6?
So you get 70 for this.
56.
Oh, sweet.
Again, that's miles squared per hour. When you divide miles squared per hour by miles, sit down.
Miles squared.
Yeah, you get miles per hour if you divide by miles. So what's the final answer?
Miles squared per hour per mile.
56 divided by 0.8 is 70 miles per hour. Okay. More tomorrow. I need to give you your homework. Make sure Haley comes back.
Haley. I can send it to her.
The homework tonight, like I said, in the front is odd. It's odd. And the answers are on at the end of the packet.
Wait, what's the shape? Is it going to push the Monday or not?
It is going to be on Monday. I just haven't updated it. Anybody else need one? Did you also take the And wait, this is.
What is your last name?
And the answer is